Hi, welcome to another video. I'm going to look at another chapter of this special publication of economic geology. This is chapter number 5. The title is Locating the Missing Half of the Giant Chuquicamata Porphyry Copper Deposit, Chile. In this article, the writers compared Chuquicamata with another deposit at south called MMH, which stands for Ministro Hills, to see if they can find missing half of Chuquicamata. Here's a summary of analytical methods have been used in this article. First of all, they've used different zircon dating methods, both ID teams and laser ablation ICP-MS, to obtain precise crystallization ages. And because they have used laser ablation and in situ methods, they could separate inherited zircon cores, which are Triassic in age, from newly crystallized Eocene zircons, which redefine the age of MMH to somewhere between 33 to 35 million years. And it's quite identical to the ages of Chuquicamata. And it's a very key point in this article because the older assumptions were that MMH is 39 million years, it's older, and it's not related to Chuquicamata. Another method being used was rhenium osmium molybdenite dating. It provided direct ages for mineralization events, which were around 32 million years, including 5 dated pulses within that period, and isochrone construction method helped to identify possible remobilization events. For example, 3 million years age have been mentioned in this article, which is linked to late faulting remobilization. Another method was fluid inclusion microthermometry, which conducted on deep copper molybdenum veins in MMH. The key findings were that homogenization temperatures and salinities, they all matched Chuquicamata, and they found halite bearing inclusions with high salinities up to 47.8%, which indicate hydraulic fracturing and overpressure. So those findings all tied fluid inclusion patterns to active faulting during mineralization, not just post-mineral offsetting. It's another key point. Lead isotope geochemistry has been done, including evolutionary corrections to Eocene ages for getting to a reliable comparison. Just to explain evolutionary correction, it adjusts current lead isotope ratios back to their values at the time of ore formation, and make it possible to confidently match the source signatures of different deposits. And whole rock geochemistry have been done. It's kind of routine methods for all these kinds of studies. Plots of these geochemical data provided a tectonic and magmatic linkage, not just spatial or structural proximity. And finally, structural geology and fault interpretation have been done. An integration of structural data with fluid inclusion in isotope systems. A key point about structural geology was the concept of sigmoid loop trap along the west fault. It has been proposed to explain why MMH wasn't displaced 35 km, just 7 km. This is an aerial map of the Chuquicamata. It's one of the largest open pit copper mines on the planet. And these sweeping traces reveal decades of excavation. And geologists have come to believe that what's visible is only the half of this mine. It's only half of the story. And somewhere in this desert, perhaps beneath under the gravel, or perhaps displaced by faulting, lies the missing half of this supergiant porphyry system. These are some regional maps of Chuquicamata. It's often shortened to Chuqui, and as I said, it's the largest open pit copper mine in the world by cumulative output. More than 125 million tons of copper have been mined there, and its deep porphyry roots are still being explored. But here's the main part of the story. For most of the 20th century, geologists believed they were only seeing half of the deposit. That's because the western margin of the pit is sharply cut by the west fault, and beyond the fault, it's just barren granodiorite, no ore, no alteration, and no clue about the rest of the deposit. Here's another regional aerial map. Interesting thing about Ministro Hales or MMH deposit was that Codelco was drilling for a waste site. They were not looking for an ore body. And then they stumbled on a major deposit just 7 kilometers south of Chuquicamata. And then sigmoid loop trap has been suggested that MMH was not displaced the full 35 kilometer away like expected. Instead, it was trapped in a sigmoid loop. It's a kind of kink in the fault system that acted like a geological catcher's mitt. It's a rare structural trap that preserved an entire porphyry system. And then there were geochemical signatures. MMH and Chuqui are geochemically twins. They have same mineralization ages, 31 to 35 million years, same lead isotopes, same salinity and temperature in fluid inclusion results. Even the high sulfidation ratios and molybdenite waning timelines and dating match almost identically. So this MMH discovery raises a bigger question, that how many trapped deposits exist in structural bulges or bends hidden under, or assumptions of just linear fault transports. Here is a cross-section of Chuquicamata. This cross-section, this is a cross-section at 3,600 meters north. It provides a rare opportunity to go through the spatial and temporal evolution of hydrothermal alteration within the deposit. As you can see, at the deepest levels, we observe the chloride zone. It's a low temperature distal alteration domain representing early fluid interactions with country rocks. Above it lies the background potassic zone. It's a remain of the system's earliest high temperature magmatic hydrothermal phases. And central to the profile is a zone of intense potassic alteration. It's overprinted by progressively cooler and more acidic fluids. And they're overprinting by pervasive and transitional quartz-cerside alteration, which indicates telescoping of the system, where later stage fluids reinterred and modified earlier mineral assemblages. These transitions record a protracted lifespan and dynamic fluid evolution, which is characteristic of large porphyry systems. A key point here is the quartz molybdenite vein zone, which includes more than 50% of the veining in some places. This zone marks the core of the molybdenite mineralization, and it's coincident with high permeability and sustained fluid flow. Overlying this zone is a distinct stratification which is related to supergene process. The red boundary, or the red line, delineates the base of stronger copper enrichment. The green line indicates the base of total sulfate leaching, and the dashed line marks the lower boundary of partial leaching. These geochemical fronts reflect vertical fluid migration during weathering and oxidation. The entire alteration sequence is structurally bounded by two major features: the west fissure, which is a long-lived regional fault, and the east deformation zone. These structures not only channeled hydrothermal fluids, but also partitioned alteration domains and influenced the localization of mineralization. And you can see that the pit profile as of December 2003 and on top, it's superimposed on the section. It shows the importance of integrating geological, structural, and geochemical data in developing an economically viable mine plan. Here we have another regional geology map. At the first glance, Chuquicamata looks like a typical porphyry system, until you notice that there's a west fault, which is a massive north-south strike-slip fault. For a long time, geologists believed it may have shifted rocks about 35 km left laterally. And this raises an important question, that what if half of the Chuquicamata system was sheared off and displaced to somewhere else? Okay, you can see that to the west and south we have deposits like Tuki, Minasur, and Ministro Hills, or MMH, which sit along the projected fault trace. This stratigraphy, igneous rocks, and alteration patterns between these deposits all match with each other. And Minasur is a key deposit here to understand the vertical evolution of the Chuquicamata system. It's located just south of Chuqui. It's an exotic copper deposit, and which is formed not by magmatic fluids but by the weathered copper traveling through ancient river beds and deposited somewhere else downstream. And the origin of copper is oxidation of porphyry deposits upstream Chuquicamata mainly. It has been uplifted, eroded, and stripped off of its sulfides during the Neogene. These exotic systems are very rare deposits like Minasur, because they need very strict conditions under which to form. Here we have a dry, oxidizing climate, which is quite unique in Atacama desert. And we have massive hypogene source like Chuquicamata upstream. And the third important factor is porous traps in Neogene gravels downstream, which enables those copper eroded upstream to deposit somewhere else within those porous gravels. Here we have geochemical plots to compare these porphyry deposits with each other. In panel A, we have titanium oxide dioxide, which plotted against the combined concentrations of uranium and thorium. And you can see that rocks from Chuquicamata and MMH are shown in red, green, and blue markers, and they cluster tightly in the lower left quadrant of the plot. So these rocks are uniformly low in titanium and uranium, thorium, and which is pointing to a chemically evolved magmatic source. By contrast, we have samples from El Abra, Fortuna, igneous complexes, and they're wildly scattered, indicating more heterogeneous and likely unrelated magmatic inputs. Sorry. And we have panel B, which shows yttrium versus tantalum trace elements. They're usually used to infer tectonic settings. And we can see once again that Chuquicamata and MMH samples cluster together within the VIG, or volcanic arc granite field. This is diagnostic of an active continental margin setting, just like subduction zones. And importantly, there is no compositional distinction between these two systems. They are geochemically indistinguishable in this diagram, and it reinforces their derivation from the same subduction zone magmatic arc around 35 million years ago. And finally, at the bottom we have chondrite normalized rare earth element patterns, which displays rare earth patterns of both Chuquicamata and MMH. They show smooth, consistent rare earth profiles. They have a clear enrichment in light rare earths, LREs, and depletion in heavy or HREs. This is a typical pattern of magmas derived from thickened crustal source, which have been modified by fractional crystallization and fluid exsolution. Again, it's a classic feature of porphyry systems. We can see in these diagrams that potassic, Triassic granodiorites, host rocks like Alena, and they plot along the same trajectory. These overlap across both host rocks, and the Eocene intrusions implies a shared magmatic lineage, or maybe it's a sign of a pervasive geochemical homogenization. Here we have dating results and geochronological diagrams. Let's start with uranium lead zircon datings. Those curved Concordia plots you see in the panels E, G, and H. You can see that instead of being all over the place, the data cluster very tightly. Panel G gives us an age of 33.5 plus minus 3.5 million years, and in panel H we have even tighter ages, 33.7 plus minus 0.8 million years. So you can see that MMH lines up almost perfectly with Chuquicamata's main magmatic phase, which is around 31 to 35 million years. And we have panel B, uranium osmium molybdenite dating results. It's one of the best ways to date actual mineralization, not just when the magma crystallized. It's a perfect method, uranium osmium dating. We can see that most of MMH samples plot around 31 million years. You can take that as the age of mineralization. And you can see a nice pattern. Samples with more uranium are still giving consistent ages. It's always a good sign that the system behaved geochemically. And we have panel C, which is the isochrone age. It's basically a way to double check the timing with the thread line. And you will notice two lines here. One gives us 31.3, which confirms the mineralization age. The other is down around 3 million years, and this is probably due to late stage fluids or maybe even sample disturbance. It's quite interesting, but it's not the main story. So what does all this mean? First of all, the older 39 million years age, that was off. It was not a real age of MMH, and MMH is as old as Chuquicamata, and structurally they were pulled apart later, but you can see geochemically and geochronologically they are part of the same system. Here we have fluid inclusion results. We have homogenization temperatures. Okay, let's start with the red dots. Here we have primary and early secondary fluid inclusions. There are little pockets of mineralizing fluids trapped inside quartz during the earliest stages of ore formation. We can see that most of them cluster around 275 to 350 degrees. They have salinities below 10% NaCl equivalent, and that's a key. Those values match what we see at Chuquicamata or even other porphyry systems like Butte. And it tells us that MMH was not some odd breccia or shallow vein. It was part of a deep hypogene porphyry system, likely formed 5 to 8 kilometers below the surface. And we can see that things get much more interesting with the yellow dots, the late secondary inclusions, which sometimes contain halite crystals. These fluid inclusion results show much higher salinities, up to 47 weight percent NaCl, and they have much broader temperature range, from as low as 127 to way up to 400 centigrade degrees, and that's a big signal. And what we are seeing in those inclusions is the fluid overpressure. It's possibly related to tectonic faulting, boiling, or hydraulic fracturing. They're all classic signs of reactivated fault zone. And which fault is that? Very, very likely the west fault, which we think wasn't just slicing through the system after mineralization, but it was actually active during ore formation, and it shaped how and where the metal ended up in the system. The photographs on the left show the actual inclusions and their types. There are different types of inclusions, you can see. And there's some key takeaways from these diagrams and these results. First of all, we have high salinity with low with high contents of NaCl fluid inclusions at late stages. And as we said, they could be related to fault activity or fluid overpressure. They suggest episodic boiling and hydraulic fracturing. And we have a broad temperature range in inclusions from, if we include the late ones, it ranges from 127 to 400 degrees. And it's kind of rare or interesting because fluid inclusion populations usually tighten towards certain depth temperatures of stability fields. And it shows a dynamic pressure cycling environment, possibly related to tectonic pulsing and remobilization of metals. It wasn't just one stable fluid event. And we have a strong overlap of these results with Chuquicamata and Butte. And it suggests that these systems were all linked together. And so fluid inclusion dataset is not just geochemically interesting. It provides evidence that the West Fault was active during mineralization and helps stitch, MMH back to Chuquicamata in a way, in a way few other data sets could. So what we can learn from this story? First of all, structural intuition is not just enough. We have big faults, and they don't always pull things cleanly. They twist, bend, and create pressure shadows, and places where ore can settle, get preserved, or can be missed. And another thing is that geology is a kind of team effort. The structure gave us a clue here, but it was isotopes, fluid inclusions, and geochemistry that sealed the case. Matching lead isotopes, identical rare earth patterns, overlapping fluid inclusion salinities, and homogenization temperatures, and also dating results. They were all chemical fingerprints. And another thing is that ore evolves vertically. Some of the weird high sulfidation zones that we can see today, they could be separate systems, or they could be the oxidized upper memory of deeper porphyry centers. And what looks exotic on the surface often has a familiar look or core if you look deep enough. And another interesting thing here was that Ministro Hales was discovered by accident. And Codelco wasn't even looking for ore. They were drilling for a waste site, and they hit big copper mineralization. So MMH and Chucky, they are two sides of the same geological story, a supergiant porphyry system split by faulting, and actually they have been reunited by science. Thanks for watching.